Let me tell you a little bit more about the motivation that led us to develop this FPGA platform that we present at PerCom. The main motivation that pushed us to develop this FPGA platform is that we have started to explore recently electric potential communication or capacitive communication. This is something that is particularly interesting because it would allow to create a short-range communication link using much less power than if you were using electromagnetic wave. And this is something that has been explored by several research groups in recent years, but we have, I believe, a particularly interesting and particularly sensitive electric potential receiver for this purpose. So currently we implement both the transmitter and the receiver in software using an ARM Cortex M4 platform, which we call BlueSense. On the transmitter side, the processor doesn't really have too much to do. It does have to encode the payload, but then the actual modulation is done using a DDS chip, a direct digital synthesis chip that generates an FSK modulation. The signal is then amplified, received by our electric potential sensor, analog filtered, and then the processor on the receiving end has to acquire the data, mix the data, demodulate the data, and decode the data. So this is something that is quite computationally heavy. Currently, with our implementation, we're able to decode an incoming bit stream at 115 kilobit per second. But this uses about 50% of the CPU power. So if you wanted to increase further the bit rate, we would have some difficulties doing that on the Cortex M4. Of course, we could use Cortex M4 with a higher clock frequency, but still using a processor has a little bit of an issue when we want to have cycle accurate timings, notably when we want to lock to an incoming clock and do the bit stream decoding. So this is actually why we considered exploring an FPGA for the digital demodulation of the signal as part of this electric potential communication project. The other motivation for this work is some exploration that we have done a number of years ago where we developed an algorithm called Warping Longest Common Subsequence. This is a template matching algorithm which we use for human activity recognition. What this equation tells us is how to update the values within this matrix. In fact, every time that we receive a sample from our sensor, we update one column of this matrix. And the last line tells us how similar the incoming signal is to a particular template which we would like to spot in the stream of data. We can see this algorithm in action here. We are going to look at the recognition of human activities, notably a drinking gesture from a motion sensor placed on the wrist. You can see the raw acceleration here, a nice U-shaped pattern corresponding to the drinking gesture, which is here filtered after a low-pass filter. You see here the matching score, which is shooting up when the person is drinking, and you see here a crisp detection of the drinking gesture. This algorithm can of course be implemented in software in a microcontroller, and we have characterized that in the past. But if we look at the details of the algorithm, we see that it can be implemented using only integer operations, and the operations that are needed are only additions, shifts, and comparisons. So this is particularly interesting if we wanted to translate that into a digital implementation, potentially as some kind of a sensor front end that would be included eventually in the future in a commercial microcontroller. So this is what motivated us to develop this FPGA platform, and we hope that in the future we can explore it for the realization of digital communication as well as embedded AI algorithms.